Hello. Tonight we're going to solve problem 39, chapter 5. Four 9.5 kilogram spheres are located at the corners of a square of side 0.6 meters. Calculate the magnitude and direction of the total gravitational force exerted on one sphere by the other three. So here we have M1, M2, M3, and M4 at the corners of a square. The distance that separates them 0.6 meters. And because of the symmetry, this problem is easier than if had these masses been of different values and the distance that separates them being different. So please follow along because I'm going to use some symmetry arguments to move the problem a little faster. Okay, first let's draw some vectors between M1 and N4, M1 and M2, and M1 and M3. Now I'm choosing M1 to be the net force on due to the other three because the forces on M1 due to the other three are up and to the right. So this makes the problem a little simpler. We don't have to worry about those components in the first quadrant. We don't have to worry about negative components. So that being said, let's make our list. So I'm going to make a list of components starting with the force on 1 due to 2 in the x direction, the force on 1 due to 2 in the y direction, the force on 1 due to 3 in the x direction, the force on 1 due to 3 in the y direction, the force on 1 due to 4 in the x direction. Hold your hats here, force on 1 due to 4 in the y direction. So there's quite a few components here. However, because of symmetry, some of these components are the same in magnitude. So we may be able to get away with just a couple of calculations to determine all the component values. So, hey, the first thing I recognize is that the force on 1 due to 2 in the y direction is 0 because the M1 and M2 reside on the x-axis. Therefore, there's no y component. It is also true that the x component of the force on 1 due to 4 is also 0. So there's two components down that we really didn't have to make a calculation. All right, let's start with the force on 1 due to 2 in the x direction. So using Newton's universal law of gravitation, g m1, m2, divided by the distance that separates them, times the cosine of the angle 0 degrees. So owing to the fact that m1 and m2 reside on the x-axis. So if you input these numbers properly in your calculator with no syntax errors, you should get a magnitude of 1.67 times 10 to the negative 8th newtons. Now, it turns out that the magnitude of force between M1 and M4 along the y-axis is the same. So I'm going to borrow that calculation from the force on 1 due to 2 in the x direction. Okay, and see for yourself. Here we have M1 and M2 and M1 and M4 equidistant, and they have the same masses. Therefore, they should have the same component value. Now, let's look at the force on 1 due to 3 in the x and y direction. Because M3 lies along a diagonal, it has components in x and y. So here we have g m1 m3 over r squared. Now, the diagonal distance is a little bit longer, and if we use some trig here, Pythagorean theorem to be specific, we have 0.6 squared plus 0.6 squared. Take the square root of that, and we get approximately 0.85 meters for the diagonal distance between M1 and M2. So that's going to be our R value. That's going to be a radial distance between M1 and M3. Now, because it's along a diagonal, we have to multiply it by the cosine of 45 degrees. Okay, again, by inspection, the diagonal along between M1 and M3 is 45 degrees above the horizontal. Okay, again, if you put those in your calculator with the proper syntax, you should get 5.89 times 10 to the negative 9th newtons. So practice that, make sure. Okay, since, again, symmetry argument tells me that the component of x and y are the same for a 45-degree angle, so I'm just going to cut to the chase here and write down 5.89 times 10 to the negative 9th. There we have it, all our components. Now, let's determine the resultant of all these components. Okay, I'm going to have a large radical here so I can park all my components. So the components are the sum of the forces in the x direction squared plus the sum of the force in the y direction squared. But because of symmetry, the sum of the x components is equal to the sum of the y components. So I'm going to simply just list the x components, add them up, and multiply them by 2. Because if I have the same sum for the x as the y, then really doubling that. I'm going to put my 0 here to represent all three components, one component being 0. So if I multiply the sum of the x's by 2, that gives me the resultant vector. Now take the square root of that. So taking the square root of the sum of the x components multiplied by 2, we get a value of 3.19 times 10 to the -8th Newton. So there's our magnitude for the net force. Now again, by inspection, just a look at that net force, which would be along the diagonal, because again, the force between M1 and M4, M1 and M2 is the same. Symmetry argues that the net force will be along the diagonal, along the line of force between M1 and M3. So the angle, or the direction for that matter, of the net force, 3.19 times 10 to the -8 newtons, is 45 degrees. And there you have it. All right, have a good evening.